Alrighty, can everybody hear me okay? Just turn the microphone on. So I'm going to be talking about observations with NIRSpec that use the microshutter assembly. And so this is work that we've been doing over the course of the last several years, putting together the overall flow of operations process for the planning. This was myself, Diane Karakala, Emily Wislowski, Elena Henry, and Leonardo Ubeda from the NIRSpec team, including inputs from the AURA and ESA JWST NIRSpec team, and also with discussion with software developers, observatory engineers, long and short-term planners, the schedulers, and some program coordinators. So we've really kind of gotten input from the engineering staff here at Space Telescope to get this MOS observing, or the microshutter assembly observing process working. And can't seem to forward that. Can't seem to forward my slides. Alrighty, so this is just kind of an outline of what this presentation is going to show. I'm going to show a very brief intro to the NIRSpec and the microshutter assembly, information on NIRSpec, the MSA-based target acquisition process, our necessary deviation from the JWST single stream observing philosophy. So this is both for MOS mode science as well as the MSA-based target acquisition. We've got some guidelines and recommendations for proposing observations that use the NIRSpec MSA. There's also a step-by-step checklist for the MOS proposal process. I've got an introduction to the pre-imaging that we have devised for NIRCam same-cycle imaging for MOS planning. And as a note, this option is not available for ERS programs. And I've also got an example use case at the end. As you can tell from this outline, this is a pretty dense presentation, and if I don't have time, I probably won't go over the example use case. But the slides, I hope, lay out the example pretty clearly, and I hope they'll be useful for people to look at. So what this presentation won't show, I'm not going to show a detailed review of NIRSpec and all of its observing modes and capabilities. For that, there was a great webinar last year by NIRSpec PI Pierre Ferrou, and I'd like to point people to that. I'm not going to do a very detailed description and review of the NIRSpec MSA hardware or the MOS observing mode. For this, there was another good webinar by NIRSpec team member James Meserole on the NIRSpec microshutter assembly back in December. And there was also a NIRSpec MOS mode presentation by Torsten Boker at the ESAC workshop. I'm also not going to go through step-by-step instructions on how to run the MSA planning tool. That was a webinar that was back in February by Diane Karakala. And there's additional information that's very useful to know for the MOS planning process, but I'm not going to cover it here because it's not NIRSpec specific. So for example, an APT demonstration, a review of the general target visibility tool and the visibility information, which Bill gave a nice webinar on a couple of months ago as well. Also kind of the structure of a JWST visit. I'm not going to go over that, but this is still going to be chock full of wonderful information. So NIRSpec is the main workhorse 0.7 to 5 micron spectrograph for JWST. It was built by ESA. The PI is Pierre Ferrou. The detector and microshutter assembly were provided by NASA. And I'm going to talk a little bit about the NIRCam pre-imaging concept that we have. And so as a result, I'm going to very briefly right here introduce that NIRCam is the main 0.7 to 5 micron imager for JWST built by the University of Arizona, and the PI is Marcia Ricci. And so for NIRSpec, we've got 4 main science modes that are carried out with 3 sets of hardware: the multi-object spectroscopy with the microshutter assembly, the integral field unit, and the integral field spectroscopy mode. And then fixed slit spectroscopy using 5 fixed slits that we have in NIRSpec. We also have another mode that uses the fixed slits for the planet transits, and that's the bright object time series. And so this is just kind of a summary of the target type and the aperture mask summary. So the microshutter assembly, you can select 250,000 0.2 by 0.46 microshutters. And what we do is we open these kind of in a column to create these little slits on science sources. And so NIRSpec's focal plane assembly, which is basically the detector system, consists of 2 closely spaced Hawaii 2RG sensor chip arrays with the 5.3 micron long wavelength cutoff. We have 6 gratings and 1 prism. And so we provide full 0.7 to 5 micron coverage in 4 grating settings or 1 setting with the prism. We've got spectral resolutions of 2700, 1000, and 100, going from kind of high to low. And we also have 1 mirror that's used only for target acquisition imaging. And so I'm going to outline NIRSpec MOS Science Node and the MSA-based target acquisition now. So as mentioned, the microshutter assembly is a configurable array of 250,000 shutters. They're these tiny little doors that are opened and closed by sweeping a magnet arm across the array. And there are 4 quadrants of shutters. They span an area of about 3.6 by 3.4 arc minutes. And this is just a little hardware view. Just see if I can use the... So this is just a little hardware view of the actual shutter doors and then the 4 quadrants themselves. So this is a flat field image taken with these micro shutter doors all configured, all open. And so you can see the reality of what we're going to be dealing with. We've got areas of failed closed shutters, and we're going to have to plan around these. Obviously, you don't want to put science sources on top of the failed closed shutters. And the interesting thing about the NIRSpec MOS mode observing is that we've got this fixed grid of MSA shutters, which means sources can't all be centered in their spectral slits. And so the planning software has to constrain your plan to be able to center sources based on your constraints that you want. And so this is just a zoomed in view of an MSA, a single MSA shutter. There are bars around them that vignette a total of about 0.06 arc seconds between the open shutter area. And so this is an example of what we call a collapsed shutter view, where all of the sources in an observing plan are shown overplotted in a single area. And so you can see that this is kind of the constrained observation there. And so this is basically the data view of the MOS science. Although we've got failed closed shutters, you can pack a whole lot of science sources in and observe quite efficiently in the multi-object mode. And so this is an example of what you see as a MOS spectrum in our medium resolution, short wavelength setting. You'll always have open fixed slit spectra that are required because the fixed slits are always open to the sky. And in this medium resolution setting, you can actually see 0 order images. So this is a 0 order image, for example, of these slits that are open over here. And so what we do is we configure the shutters in an open column on science sources to measure their spectra of many items or many targets. So quick summary of the NIRSpec target acquisition using the microshutter assembly. The MSA-based target acquisition uses the area in imaging mode to observe between 5 to 20 reference stars. And so these reference stars are used to correct the initial pointing and accurately align the science sources within the MSA shutter. So this is kind of standard MOS-based target acquisition, where you need to observe sources throughout the field, determine where they are in your image, compare that to where they should be, and correct the pointing, and in our case for NIRSpec, the Orient. So the MSA-based target acquisition can be used in MOS, IFU, or fixed slit observing modes to give estimated target positioning accuracies on the order of 20 to 60 milli-arc seconds. And the accuracy of this TA depends very significantly on the input source catalog position, the astrometry that you use to plan the observation, your science sources, as well as these reference objects.
assume that the reference objects are well centered in their slits?
So there's a question, does this assume that the reference objects are well centered in their slits? So the reference objects you don't have, let me go to the next slide actually. So basically the second bullet point here kind of it describes the operational procedure for the target acquisition. So the TA process, which is called TAC in APT, this observes the reference stars through the all-open MSA in one exposure. Then it offsets the telescope by a half shutter pitch in both X and Y, so that if you've got reference stars that are behind those mounting bars of the MSA, you'll be moving them to basically be in the middle of the shutter. And so it takes that second exposure to mitigate the effects of the bars that we have in place. And so the planning software is going to plan these sources so that they're away from failed closed shutters, because the failed closed shutters or regions of failed closed shutters are going to be problematic for this operational procedure, but the MSA grid will not be. And so the best slew and orient correction to precisely align the science sources in their planned MSA shutter is derived using these reference sources and then executed on the telescope for the TA. So this is just a plot of the target acquisition estimated accuracy as a function of input catalog astrometric accuracy in milliarc seconds. So for example, if you've got 10 milliarc second astrometric accuracy, like from a wonderful Hubble image, then you can get up to 20 milliarc second accuracy in your delivered target acquisition for your science sources, and that is 1/10 of a shutter width for us. And so these colored curves show the number of TA reference stars. There's not a very large spread between the performance between 5 to 20 reference stars, but you can gain a bit, particularly between 5 to 8 reference stars here. And so the plan is to use these reference stars and correct the pointing with planning catalog accuracy from 5 to 10 milliarc seconds out to possibly 50. And so now I'm going to talk a little bit about the NIRSpec MOS observing process and the deviation from what's called the JWST single stream observing. And so a highlight note I just want to mention, in cycle 1, ERS, GTO, and GEO observers that wish to use the NIRSpec MSA either for MOS science or for target acquisition, you will not be submitting on-sky executable programs at the proposal deadlines. So upcoming proposal deadline for ERS and GTO in August, and also for the GEO deadline next February. The programs that you submit will not be completely specified and executable. And so the goal of the single stream process for all programs is that submitted proposals should be schedulable. So that means that they have time requests and pointings. The hope is that some of the simpler programs can be ready to execute when proposals are submitted. NIRSpec programs that use the MSA can't be executable at proposal time. They need to be schedulable following the single stream. But we do have to have an update process for all programs that use the MSA. And the reason for this excuse me, is because accurately aligning those NIRSpec science sources in their little microshutters requires very well-calibrated astrometric field distortion information, which we will not have until after JWST commissioning. We've never taken an image off from NIRSpec focal plane all the way out to the sky, so we don't have the full distortion, and we can't accurately place sources in the shutters yet. And so the NIRSpec MOS science and MSA-based target acquisition programs will require this two-stream process with an update after the proposal deadline. And so there's also a philosophy for having this deviation from the single stream process, because NIRSpec programs that use the MSA either for MOS science or for target acquisition must have a very fixed orient at the time those programs execute to ensure that the science or TA sources are where they need to be in order to carry out the observation. And so in general, proposals that are submitted with very hard orient constraints are difficult to schedule with very narrow available observing windows. And so for folks that are familiar with APT, This is just a visit planner view of the APT observation for an example highly constrained visit. This is a Candles UDS visits at a 48-degree aperture orient with 0 range. You want to plan it at 48 degrees. This observation can only be scheduled for this 8 days from September 2nd through September 10th of 2019. So you've got a whole year observing cycle, but you can only schedule it for 8 days. And that is really constraining for the long-term plan and for the scheduling. So proposals that are submitted with these very hard or fixed orient constraints are difficult to schedule with very narrow observing windows. So as an example, this is what I just showed, the very constrained observation with only an 8-day observing window. And this is the exact same visits with that special requirement of 48 degrees with 0 range removed. And so what you see here is that this opens up the schedulability for this observation for this visit from 8 possible days to 54 possible days between July and September. So it really opens up the scheduling possibility and will make it easier for programs to be placed in the long-range plan around other programs. So basically, the point is we are planning to carry out a multi-stream NIRSpec observing process for programs that use the MSA for all JWST observing cycles. And so this is so that the long-range plan made from the accepted JWST observing proposals will assign orients for programs for the majority of MSA-based science or target acquisition programs. So we've done a bit of investigation, and we've shown that some sources may require a constraint on the observation orient. So for example, if you've got an elongated source with a source position that's in a specific elongation, then you might need some sort of constraint on the orient. For schedulability of programs, we recommend that you use a minimum range of 30 degrees on an orient special requirement request in the NIRSpec MOS proposal process. So you've got some nominal orient that would be the best, plus or minus 15 degrees from that is what we recommend, and I'm going to say a little more on this later. And so it will be discouraged, but not forbidden, for users to submit one of these MSA proposals with a very hard orient request. There might be a science use case that we haven't thought of that needs this. It will have to be based on the science and justified to the TAC. So this is basically the proposed flow for NIRSpec MOS programs programs that use the MSA. And so this is kind of our multi-step observing process. So you start out with the cycle proposal deadline. The NIRSpec programs requesting MSA use need to have placeholder observations in their APT files, preferably not a fixed orient, and you need an on-hold special requirement. So the cycle proposal deadline happens about roughly 3 months before the TAC. The TAC meets, accepts the programs, and after programs are accepted, the JWST observing cycle kicks off with long-range planning, where programs are kind of placed in this long-range cycle plan. And when that happens, the scheduling windows that are fit and tailored specifically to the program will be used in order to assign an orient to the MOS programs. And so basically, we go from submitted visits in the proposal to this process of updating those visits so that they have assigned orient and can be executed on the SCI. So that process, we're calling it from planning visits or proposed visits to flight-ready updates or executable flight-ready updates. And so once a program is assigned this fixed executable orient from the long-range plan, that will be communicated back to teams, and we'll have some time here for the PIs and the program teams to update their observations and work towards that fixed orient and get the completely executable visits ready to go. The flight-ready visit updates are due about 4 weeks before the JWST MOS or MSA TA science observations are executed. So there's this little kind of span of time right here that is roughly about 4 weeks. And so during that 4 weeks, We'll have instrument team contact scientist reviews, program coordinator reviews, and the short-term scheduling needs the visits at least 2 weeks before the visits execute on the sky. So the NIRSpec, MOS, or TA observations that use the MSA execute within this scheduling window, and so this is basically how the overall process will flow. And so my next slide is basically just a text summary of what I just showed, basically for people that just download the slides on the webinar and don't watch the presentation. I wanted to make sure that the text is clear and you can make sense of the presentation without watching the video. So now we've seen the multi-phase observing process for the NIRSpec MSA-based observations. And so this is just a summary of the MOS mode and MSA-based TA, kind of a step-by-step checklist for proposers. And so I started out with a slide that showed a heck of a lot of text and got into some details of discussion on the APT parameters that you might not be able to understand if you don't have APT right in front of you. So I actually have that slide on the next one, and I'm just going to gloss over that because it's a whole lot of text. But it was recommended that I change that to a flowchart that's maybe a bit more digestible in a presentation. So this is kind of the step-by-step flowchart of observations for this, proposing for this multi-stage NIRSpec. In this particular case, I'm talking specifically about MOS science. So you've got this awesome NIRSpec MOS science idea. You download and install your APT. That's kind of a first step for JWST observations. And for NIRSpec MOS, you don't really fill out the APT template like other observing modes. So other observing modes, you go into the template and you pick your grading, you pick your exposure time, and you fill out these very concise parameters within the interface. For NIRSpec, we use the MSA planning tool, MPT. And so this is a webinar that Diane Karakala gave it back in February that describes the step-by-step process of using the MPT and what you can do to get an observation plan from that. And so you use the MPT, and in order to use the MSA planning tool, you need to have a catalog of the MOS field that you want to observe. That's actually kind of step one for any MOS-based observations. You need to know the sources that you want to acquire spectra of. So you need to construct, derive, or simulate your planning catalog for the science. And you ingest that into the MSA planning tool. And kind of a not NIRSpec specific step that's very useful is to use the visibility tool either in APT or the general target visibility tool that Bill Blair demonstrated a couple months ago to check the available orients for your catalog observation. And so you plan your observations in MPT using your catalog. And what we recommend is that people test this at several different available orients to understand the constraints on your observations and understand how much time it's going to take at different orients to actually execute your science. And so you need to really understand the multiplexing and the results that you're going to get. I think I didn't highlight it previously, but I will now. We've found that for the vast majority of catalogs, the orient is not a significant driving factor on the multiplexing performance. So after you've done this at a couple of different orients and filled with the parameters and understand what you're going to get, you use the MPT and you use a button there that says Create Observations. And so what this does is it takes the observations that you summarized in MPT and it populates the template with that information, with the pointings, the MSA configurations, the exposure parameters. So the items that you would, in other templates, just fill out, MSA populates everything for you. And for scheduling, we recommend no special orient requirement. I need to grab a little water really quick. Okay. So for scheduling, we recommend no special orient requirement. MSA-based MOS science programs need an on-hold special requirement. And for all programs that use MSA-based target acquisition, the TA reference stars do not need to be in the proposal. And the reason for that is because when you're planning your MOS planning visits, you're not necessarily at the exact pointing that you're going to wind up at. And because your orient might change, if you planned your TA reference stars when you do your flight updates, those stars might not even be in the quadrant field. So it's just extra work for people to plan their target acquisition observations at the proposal time. And we don't want people that are just in general submitting proposals to have to go through that process. And so after you've done these main steps, then you're ready to submit your proposal. And so this is, again, just a summary of the flowchart bullets that I just went through. Some of this has expanded text that, like I said, might not make sense if you don't have the APT right in front of you. I use this as reference for people to take the slides and hopefully help them plan their observations as they're going. And so I do just want to mention really quickly that the previous flowchart was specifically for Moss Science. For the target acquisition, for IFU or fixed slit science programs that want to use this MSA-based target acquisition, you are going to require planning catalogs of sources for TA when you do your updates, not when you write your proposal, but when you do your updates. And we just want to make sure that people know that. The MSA-based target acquisition needs those reference stars. So you need the reference stars anchored to the position of your source for the fixed slit or IFU science. And so the NIRSpec spectroscopy should not have a special requirement. So this is fixed slit or IFU spectroscopy. You also shouldn't constrain the Orient. You also need the on-hold for Orient assignment special requirement. And then the target acquisition reference alignment targets or reference alignment objects do not need to be in the proposal. So this is just a little flow chart for your awesome NIRSpec IFU or fixed slit science idea that needs the MSA-based target acquisition. You fill out the appropriate template for your science. We recommend no special Orient requirement. The MSA-based target acquisition programs need your on-hold special requirement. And then the target acquisition reference star parameters don't need to be in the proposal. So it's really just adding a special requirement for the on-holds after you filled out the template is what you need to do for these programs. So I just want to summarize really quickly what affects multiplexing in the NIRSpec Moss Science mode. So there are a number of things that affect the multiplexing, sometimes in ways that you didn't really quite anticipate. Obviously, the MSA operability affects the multiplexing. All those failed closed shutters, if you can't open the shutter, you're not going to be able to acquire spectra on the source there. So that does affect the multiplexing. The catalog size affects the multiplexing. If you've got a catalog of really high priority objects that there's only 80 targets in the catalog, you're not going to get 200 targets in your plan. So that's kind of an obvious thing. The catalog density affects the multiplexing, and it turns out that plans max out the open shutter space at roughly 800 to 1,000 targets per square arc minute. So if you've got that many targets, your first configuration is going to be basically maxed out. You're going to have shutters open on science sources pretty much everywhere. And so the catalog spatial extent and coverage is going to affect the multiplexing, for example, clustering or target distributions. So this, of course, extent and coverage kind of has catalog size and catalog density wrapped in there. But clustering and basically the distribution of elongated sources affects things as well. And so the disperser, the prism mode has higher default multiplexing. And so the reason for that is because the prism mode spectra in NIRSpec are only about 500 pixels long, and it turns out you can get more of those across a single observing row than you can for the gratings. The gratings only have long pass filters, so you wind up with second and third order contamination in some positions, and so you can't observe sources on the same spectral row without contamination. And so just a quick view of program. So this is an example grading observation in a dense field. So what I'm showing here is an MSA planning screen view of an observation. And so the green dots represent sources that are in open shutters with the configuration that I requested. In this particular case, it was a 3-shutter slit. And so these are the sources that are observed in this program. And the orange depicts open spectral open spectral rows, essentially. So this is an area where flux is dispersed onto the MSA area, the detector area. The red lines are failed open shutters that we plan around. And so what you see here in this example configuration is 66 targets observed with no spectral overlap. This was in a very dense catalog, so we were able to plan 66 sources with 3 shutters and really kind of max out the observing space. It actually turns out that in prism mode, because of this increased multiplexing, this exact same field, same input catalog, but using the prism, you get 240 sources in a single MOS plan. Again, these are green objects are the sources that are observed, and the orange is basically showing the region on the detector that will have spectra. And so you get 240 sources, a single pointing with no spectral overlap. So the MOS multiplexing with NIRSpec can be extremely high with prism mode. And so an additional item that affects the multiplexing is the MSA slit shape used in MPT. In the previous example that I just showed, I was using a 3-shutter slit, but we've got 4 different options in the MSA planning tool. You can select basically the slitlet configuration that you want for your science for very extended sources, compact sources, and the multiplexing basically is coming from the slitlet shape that you adopt. So in a single 1-shutter configuration, you get 176 targets observed. Again, this is a catalog that has a high density of sources, so we're really maxing out the configuration. This is 176 open shutters on targets. The 2-shutter configuration, we've got 198 open shutters on targets on 99 of those targets. So you're not getting quite as many sources, but you're getting 2 shutters on each of them. And the 2-shutter configuration allows you to also nod back and forth between the positions. So for example, if you want to dither to take out any detector effects or even out pixel-to-pixel variations, then you can do that with these shutters. So in 3-shutter configuration, this is the observation that I just showed in the previous slides, 66 targets, 198 open shutters, and then in the 5-shutter configuration, we maxed out at 41 targets, which is 205 open shutters in the plan. So the reason why we don't have more sources than this is because it actually turns out that there is some curvature to the spectra, and the spectra don't lie evenly across MSA rows, so it actually turns out that there's a little bit of padding that you have to put in to ensure that you don't have overlapping spectra in the data. And so an additional item that affects the MOS multiplexing is the source centering constraint in the MSA tool. And so the source centering constraint, as I showed earlier in the presentation, is a definition of how close to the edge of the microshutter you want to put your science sources when you center them up in the plans. Oops, sorry. So basically, we have tightly constrained, which centers sources right in the inner region. And so tightly constrained, the definition of this is if you've got a perfectly centered source, and this tightly constrained setting will place sources in an area of the shutter where you get 90% of the flux throughput compared to a perfectly centered source. So your aperture slit loss in this region will be 90% of the perfectly centered source. So constrained is a similar definition. This is 75% of the flux of a perfectly centered source. And I should emphasize that this is point sources, because of course, extended sources with strange distributions, you might have different allocations there. And so the midpoint is 50% of the flux of a perfectly centered source. The open shutter area is just putting a source in a shutter if its main catalog coordinate is within that open shutter. So it's no constraint on the actual flux throughput, and then unconstrained can also put sources behind the position of the MSA bars. And so this is a situation that you might use if you've got sources that are very extended with even flux distributions in the inner regions, like for example, sources that are like an arcsecond in extent where the actual centering doesn't really matter as much. And so that was just kind of a demonstration of the basically the source centering constraint. This can affect multiplexing, and so these plots over here are 3 plots that show on the bottom the tightly constrained multiplexing level as a function of catalog density. So this is the number of sources in one configuration, the sum over 2 configurations, and the sum over 3 configurations. And so if you have a low source density, you'll get basically maybe about a 20% improvement in multiplexing going from tightly constrained to unconstrained. So I'm sorry, that's open shutter area, from tightly constrained to open shutter area. And so you see in 2 configurations, you can gain, again, about 20% of the sources. And so basically, if you open up your shutter area, you can gain in sources, but you're relaxing the throughputs. So relaxed source centering constraints translate to increased aperture flux losses. And so at low catalog target densities, you can get more sources by relaxing those centering constraints. At high target densities, it turns out you've got so many targets to choose from that you can max out the shutter space even with a constrained plan. And so there's less of a gain at high source densities there. And so this
is one of those defaulted?
I think the default is the midpoint, is my recollection. But that's a good question. I don't quote me on that necessarily. So. Alrighty, so also an item that affects the multiplexing is the MSA search grid step size in the MSA planning tool. So the search grid step size is the spacing of grid points that the MSA searches, the MPT searches through for targets. So for example, if you've got a catalog that's 3 arc minutes by 3 arc minutes in extent, it kind of well covers the NIRSpec footprint, and you've selected a search grid step size of 10 arc seconds. You're going to do a search for targets in optimal plans every 10 arc seconds across that 3 arc minute by 3 arc minute field of view. So you're going to do a couple hundred calculations to determine what position will have the best number of science sources in the multiplexing. So for search grid sizes from 20 arc seconds down to 0.2 arc seconds, this is as a function, the color plots here are a function of source density. And basically what you find is that going from this factor of 120 arc seconds down to 0.2 arc seconds in total, you can find optimal pointings that can get you more sources on kind of a 10 to 20% level. So for each curve, you're kind of increasing along here at a 10 to 20% level. There is kind of a space between about an arc second to 8 to 10 arc seconds where you don't really tend to gain a whole lot. It's just a couple of sources here or there. But if you go to the fine grid searches, you can acquire more sources because you're just finding the best position a little more accurately. It actually turns out that fine grid searches can take a very long time to run in the MSA tool. What I typically do when I'm doing searches is I try to do my default plans with just maybe a couple of thousand search grid points to make sure that the plan runs in a good amount of time. But then once I find the parameters that I really want to do, then I'll go in and I'll run at a finer grid search and maybe get an optimal plan. It can take a long time to run, and so I would recommend that you kind of do a coarse grid to find the parameters that you want to do, and then run a fine search to try to grab as many sources as you can. And so this is basically for a statistical survey of this number of sources in your catalogs. And so finally, in most cases, we found that Orient does not strongly affect the MOS multiplexing. This is actually something that we found a good number of years ago. Team member James Meserol did a test and found that the variation from MOS multiplexing going from one Orient to another on even distributions of sources, whether clustered or unclustered. I say even distribution, I mean isotropic in angle distributions, whether clustered or unclustered, varies by a few percent at most as a function of Orient. So if you don't have an elongated source in one direction, then the orient is not going to affect your plans very significantly. And I'll actually show this in the use case that I run at the end. So NIRSpec team member Elena Henry showed did an observing scenario on a 30 arc second extent gravitationally lensed arc. And so she ran a couple of plans and opened shutters on knots within this arc. And she learned that some planning orients aligned the arc along the dispersion direction. And that was very bad because you had to open shutters basically one by one practically in order to cover the full arc along the dispersion direction. So that is a situation where you don't want things aligned that way. This is a source that was a high enough ecliptic angle that you were able to get a wide range of orients to test. And there was clearly an optimal orient and a range around that optimal orient of plus or minus 15 degrees, which gave nearly identical multiplexing results. So that's where this recommendation of a 30-degree minimum recommended range for schedulability came from. And we found that tests on other elongated sources suggest similar performance. So you can envision a jet outflow from an AGN or a young star that's elongated, or a number of other possible elongated source distributions. And if you can find a good orient and select a range that's plus or minus 15 degrees from that, that's the optimal situation for scheduling. So we recommend this special requirements have a minimum range of 30 degrees, and that's where that came from. So basically, MOS mode multiplexing with NIRSpec is extremely dependent on your specific science program goals and the requested parameters, the slit shape, the source centering. We can't tell you how much time it will take, for example, to plan a 1,000-source survey. A 1,000-source survey of what exposure time, what gradings, what constraints. It could be planned many, many different ways. And so the NIRSpec MSA tool is really the primary planning tool to derive the time requests for proposals. And so for expanded information on the MPT and the demonstration of actually selecting all these parameters and running it, I definitely urge you to see Diane Krakala's webinar. Or come to the proposal planning workshop next week. So I wanted to talk a little bit about the catalog accuracy for NIRSpec planning and this concept of NIRCam pre-imaging observations that we have. So the performance of the target acquisition depends on those input planning catalog coordinates. If your input catalog coordinates are 50 milliarc second accuracy, you're not going to get better than about 60 milliarc second accuracy on your TA, because it's not just the number of reference stars you have, it's also the accuracy of the science source that you want to place where you want to place it. So it's not just a root increase in the accuracy. The optimal TA planning of less than 20 to 25 milliarc seconds, which is about 1/10 of a shutter width, on science sources can be achieved using input catalog relative astrometric accuracy of 5 basically to 15 milliarc seconds in the error budget we predict. Relaxed accuracy in the target acquisition, so up to this kind of 50 to 60 milliarc seconds, can be obtained using poor catalog coordinates. This relaxed accuracy, 50 to 60 milliarc seconds, that's a quarter of a shutter width at that point. And so you really basically have to have a very extended source if you're using MOS mode for this. It's recommended only for very extended science targets that will fill the MOS slits or for science observations with the IFU. And it turns out that planning catalog accuracy translates to this target acquisition accuracy, which actually then translates to flux calibration and slit loss accuracy, because the slit loss accuracy depends on how well you know where your source is in the shutter, of course. And so here I'm revisiting those shutter planning constraints that I mentioned earlier and showing the tightly constrained situation versus a completely unconstrained situation there. And so what I'm plotting here is your planning catalog astrometric accuracy for target acquisition in milliarc seconds from 5 to 50. and the estimated worst case excess MSA slit loss error for a point source. And this is a little bit to wrap your brain around, but what this basically means, for example, for a planning catalog where you've got 10 milliarc-second accuracy and a tightly constrained plan, the estimated slit loss accuracy is going to be about 12 milliarc-seconds. Because if you've got, for example, a source that's up here in the corner and you have a 10 milliarc-second uncertainty, that's going to translate to 20 milliarc-seconds in the target acquisition, so that could be your source is there or your source is there. But you do not know exactly where it is in the shutter, and that translates to not doing the correct aperture slit loss. And so this is basically the worst case excess slit loss that you don't know about because you don't know your centering as well. So you can see in basically the more relaxed input catalog accuracies, you can get calibration uncertainties because of slit loss errors on kind of the 40% level, 40 to 50% level. And that's simply because your offset from the target acquisition might put your source outside of where you think it will be. And these numbers are kind of similar between the constrained and through unconstrained cases because you've got a very steep slit loss gradient along there. So as you move just a small amount, then it can be kind of consistent there. And so a key point is that if you want the best accuracy of your flux calibration, you need kind of good astrometric accuracy observations, and below kind of 10 to 15 milliarc-seconds, HST, I think, is one of the only games in town. We've done a little bit of investigation, and some of the ground-based wide-field imagers that cover the NIRSpec footprint and the NIRSpec field of view really kind of at best get down to 25 milliarc-seconds accuracy. And of course, AO-fed instruments can get exquisite in-field astrometric accuracy for very small regions, but the calibration of the wider fields, kind of multi-conjugate imagers is not yet quite where we need it compared to HST. So in quick summary of HST catalog coordinates for NIRSpec observation planning, this figure that got skewed a little bit, courtesy of NIRSpec team member Leonardo Ubeda, shows the JWST NIRSpec quadrant footprints as well as the HST ACS wide field camera, the HST with C3 UVIS camera footprint, as well as the HST with C3 IR camera. And so this relative coordinate accuracy is important. Any absolute offsets in your astrometry are actually taken out by the target acquisition. And so with C3 IR, a single pointing of the with C3 IR camera spans only about 1/3 of the available NIRSpec open shutter area. So you're not going to get the best multiplexing if you only plan your observations with the with C3 IR positions. ACS and with C3 UVIS span a good fraction of the NIRSpec MSA quadrants and can be used for catalog planning coordinates. Single with C3 IR pointing accurately anchored in reference to a wider catalog could also be good. And HST mosaics with good relative internal coordinate accuracy are really excellent for NIRSpec MOS planning. So we've got this concept of pre-imaging for NIRSpec, and for multi-object spectroscopy, pre-imaging refers to acquisition of images in the same observing cycle or observing semester with the same telescope. Not necessarily the same instrument in the case that we've described here, but this is in order to accurately plan the MOS observations. And so pre-imaging might be needed to ensure that science targets for spectroscopy can be optimally aligned in their slits for the best flux calibration. And so use of same telescope can limit the inconsistencies between astrometric catalogs and calibrations. For NIRSpec, we need high accuracy astrometry to plan the MOS science in the tiny shutters. I consider high to be what we've talked about so far. We need better than 50 milliarc-second accuracy. Better than 15 is going to give the best calibration accuracy. So we've developed this concept of pre-imaging acquired with NIRCam in the same observing cycle to plan the NIRSpec MSA science, MOS science. So this is, again, a view from NIRSpec team member Leonardo Ubeda of blue is a NIRCam long wavelength channel mosaic, a 3-point dither and a 2-position mosaic. And red is the NIRSpec spectroscopy footprint of the microshutter assembly. And so basically you can see here that the NIRSpec MSA can be positioned at many different orients across this source using the NIRCam catalog imaging. So pre-images should, again, not be submitted with a hard fixed orient special requirement. They should be acquired to cover the NIRSpec MOS footprint at a wide range of observing orients. And a pre-imaging plus MOS visualization tool has been created by Leonardo Ubeda, and we plan this for public release in 2017, in summer. So a question that I think people have that people are a little bit confused about is whether or not they are required to get this pre-imaging, and the answer to that is no, not at all. NIRSpec MOS programs are not required to acquire the NIRCam pre-images. They're basically as needed for observation planning. HST is great, but if you want good flux calibration accuracy and you do not have accuracy, in-field relative accuracy down to that 15 milliarc-seconds, this is an option. And so NIRCam pre-images for NIRSpec must be requested in the proposal, and the time for the imaging justified to the TAC. There needs to be a reason for it. The JWST exposure time calculator should be used to estimate the science time necessary for your NIRCam pre-images. The pre-images that are required to provide infrared catalog coordinates for NIRSpec spectroscopy, only the catalog information, will have no proprietary data access period. So if a science reason is given to derive or to acquire the images and is justified, then the pre-images can be assigned the standard proprietary time of 12 months. And so the NIRCam, again, this pre-imaging option is not available for ERS, NIRSpec, MOS spectral planning because of the time necessary for the turnaround. It will be available in cycle 1 for geo observers. And so this is basically that same flowchart, but now for the pre-imaging included. And so the flowchart, basically you need to submit those schedulable programs, in this case with both the NIRCam observations for the imaging and the NIRSpec science observations at the proposal time. You've got a time frame between the proposal submission and the GeoTAC meets. And then again, the long-range plan is constructed, and in this case, the NIRSpec MSA programs are assigned to fixed execution orients, and the NIRCam observations, the imaging observations, are also assigned to scheduling window. And so at some point within the hopefully early part of the cycle, well, it depends on your target visibility, at some point your JWST NIRCam pre-images will be observed, and the data will be reduced and made available in the archive. We are reserving an option of contact scientist assistance for NIRCam mosaic and catalog verification, completely optional. NIRSpec spectroscopy planning starts for teams as soon as the images are acquired and the catalogs are verified. And then there will be a frame of time when the teams have the opportunity to plan their MOS visits. And again, there is a spectroscopy flight-ready visit updates due before the window for the MSA spectroscopy is observed. And again, this is for contact scientists, program coordinator verification, and short-term scheduling. This is about 4 weeks. And the NIRSpec MSA visits execute at a fixed orient with their available scheduling window. And I just wanted to mention that right now, the minimum time between imaging release and spectroscopy observing windows is estimated to be, at recommendation, 60 days. And this is 32 days for user spectroscopy planning and 28 days for STScI checks. And so the minimum possible turnaround time right now that we're kind of proposing for cycle 1 is 42 days, which is just 2 weeks for team observation planning of the spectroscopy. So as we get better at this after cycle 1, we'll revisit these numbers, but right now we recommend 60 days, and if you're really gung-ho and think you can turn things around quickly, we can do as short as 42 days.
And also, of course, it depends on your target visibility.
Yeah. Yeah, absolutely. The reason this is 42 days is if it's possible to observe the imaging at the beginning of a visibility cycle of a source in the ecliptic, and then the spectroscopy at the end of that visibility cycle. Ideally, that's a goal that we would like to meet. In cycle 1, we're going to be learning a lot about this process, and so, yeah. So this is basically just text talking to the previous flowchart. And so I'm not going to go over this again too much. Again, this is for people that are just looking at the slides and not watching the video of the webinar. This is kind of point-by-point instructions of what you need to do to get these NIRCam observations ready to go. There's particularly, you need to use a catalog to plan the MOS visits at the proposal deadline. So if you don't have all the information that you need to maybe simulate a catalog of sources that you might want to observe. So you need to have the schedulable NIRCam imaging observations and a placeholder for this schedulable NIRSpec MOS visits in the proposal. And so this is just going through that. There's also some special requirements for timing links that need to be added, and this is just describing that. And the blue points are the points that are specific to the items for NIRCam pre-imaging. And I'm not going to go through this in detail. So I've got 2 minutes left. I think I started a little bit late, but do people want me to go through the use case really quickly? So there's maybe like eight slides here. Alrighty, so I'm just going to describe a use case that was basically an ERS-like MOS science use case. This already has planning catalogs from Hubble images from the CANDLES survey. This is a wide, shallow spectroscopic survey of the CANDLES UDS field. And so the CANDLES UDS catalog, it spans about 22 arc minutes by 12 arc minutes extents with 40,000 plus parent sources. So this is actually the biggest catalog I've ever tested MPT with. It's not monstrously huge by overall Mosaic standards, but I was very happy that it runs with basically, I didn't log the time of plans that ran here, but they were reasonable. It was on the order of minutes, not hours. So it's good to know. So basically, in this plan, I'm observing a 3-shutter slit with nods at 1,000 seconds per exposure, 3,000 seconds total per spectral configuration. I'm using the midpoint source centering constraint under the assumption that my CANDLES sources are slightly extended and they don't need the really tight constraining limitation there. I'm using prism and medium resolution gratings, the short wavelength and medium resolution, and medium wavelength gratings at medium resolution to get 1 to 3 microns. So that's basically 3 spectral configuration settings. And the goal is spectra on at least 1,000 sources at a filtered magnitude and redshift. So basically, I took this full catalog of 40,000 parent sources, filtered it down for sources that are between, I think it was 22.5 and 24th magnitude, and then redshift of, I don't remember, it was like 0.5 to 2 or something like that. And it turns out that there's 4,600 sources in my filtered list over this extent, which turns out to be it was roughly about 25 targets per square arc minute. And so I also included a catalog that was filler targets of some brighter galaxies. And so that's basically the plan constraints. What I did after I decided what I kind of wanted to do with this program, and I did fool around with the ETC to understand the sensitivities that I would be getting on those exposure times for those brightnesses that I selected, was I input the catalog into MPT, and I saw in MPT the average catalog position, and I used that in APT to check the Orient availability. You can also take that average catalog position and use the general target visibility tool what you really need to do is check the Orient availability. And this is basically the Orient report that you get from the visit planner. And you can't read it, the numbers are probably pretty small there, but this shows the date range and the V3 position angle range. So V3 position angle is the telescope position angle in the telescope V3 coordinate, V1, V2, V3 coordinate system. And what I found was that the candle's UDS has a narrow available Orient range. It's 23 to 53 degrees in aperture position angle. So it turns out that this field, by default, only has that 30-degree range even possible. And so that was another reasoning for thinking about the 30-degree range. The 30-degree range is basically consistent with sources that are constrained at the ecliptic that only have that 54-day observability window. And so the NIRSpec AP is actually just the V3 PA plus 138 degrees. That's just kind of where we're at, because we're rotated a little bit with respect to the V3 in the focal plane, V3 axis. And we need to run the MPT to test plans at several available Orients in this 23 to 53 degree aperture range. And so what I did was I ran a short example test plan just to get a feel of what's possible for me to get. And so I've got, yeah.
I'm sorry to interrupt you. It looks like somebody has their hand up.
Okay.
But I don't know if they can actually answer or ask the question. For the person with their hand up, I don't know if that's a mistake or not. Yeah, if you have your hand up to ask a question, could you type your question into the chat session? Maybe we should just keep going until I see the question.
Okay, so I ran this initial check plan. I didn't want to run it, on a huge extent and derive my whole survey because I just wanted to learn how many sources I might get in one configuration. And I found an average of about, I think I ran it on maybe five configurations. I wanted to test it at a couple of different pointings. I found an average of about 45 sources per MSA configuration. And if you recall, I've got basically a source catalog density of about 25 sources per square arc minute. And 45 is roughly where you're going to be with that catalog density in your multiplexing. And so in order to do my 1,000 source wide field spectral survey, I need 23 MOS configurations to carry this out. So I reran the MPT with a specific 30-degree aperture position angle and 23 configurations. So this is where you input the aperture position angle. And I requested 23 MSA configurations. That's going to give me 23 individual target sets. The result was 1,027 sources observed. So I can check off, I got my 1,000 source survey there. And so then what I did was to test the effect of the Orients. I reran that same plan at 2 additional Orients. I used 29 degrees and 48 degrees to kind of span the range of that 23 to 53 Orient range that's even possible with the candles survey. And I found in one plan my 1027 sources, in the next plan 1024, and in the third plan 1033. So we're varying by 2% at most, 1%, whatever. And basically this program is the science time overall, the science time is 19 hours, the execution time is 43 hours, the program efficiency is about 43%. The reason why the efficiency is a little bit low is because every MSA configuration, because we've got this huge candles field, you're really going to a new position at every visit, which requires a guide star acquisition and a little bit of overheads at every visit position. And so basically the observed sources, these specific observed sources are different between plans, but the execution Orient has little effect on the numerical results of the large majority of statistical MOS surveys. And so that's really a take-home point that we found. So I created observations on all of the plans, and I found that the results are extremely similar. You get 23 visits, and they all take the same amount of time to execute. And so in the MSA planning tool, I created the observations while my preferred plan was highlighted, and that over here populates the MOS templates with all of the parameters for that observation. So basically, it populates all the exposures I requested and the MSA configurations for all 23 configurations. So you don't have to go in and type all or select this all from the pull-down menu for every single exposure in your 23 configurations. And so, so basically, it populates everything for you, and we just have to run the MSA tool. And so then at the end, I added my on-hold special requirement to the MOS Science program. So in my observation, there's a tab here that's called Special Requirements. I clicked Add on the explicit requirements and selected the on-hold. And so the comments in the on-hold is on-hold for Orient assignment. And so basically, I have populated the template, added my on-hold requirement, and submit the proposal. So 1,000 source spectral survey in the Campbell's UDS. Damn. So, any questions?
So your example made this more clear, and I just want to, and it's probably obvious to everybody, but I just really wanted to highlight the fact that what you're doing up front is scoping out how many configurations you need, how many observations you need, how much time you need, and that users shouldn't sweat the details of which targets exactly they're getting and whatnot in that first phase, because it's all going to have to get redone for real in your second phase of things, right? So, and like I said, it's probably obvious to everybody, but I think it's really good to just say, don't obsess over the details of exactly which targets and whatnot at that phase. But it's also quite tricky then. In this case, that was a good example to kind of say, this is what I'm assuming for my observing times and whatnot, but you're going to, those are the times you're going to have to work with in your phase 2. So you have to take some care in figuring out what kind of times for your configurations you need, especially if you're looking at a range of target brightnesses or whatever. You have to kind of put in a reasonable set of configurations so that you'll have the flexibility to do what you really want to do in the phase 2. Is that right?
Yeah.
Yeah.
Yeah, so as I mentioned throughout the talk, basically there's things that you can do to tweak the input parameters and gain 10 to 15% of the sources. I didn't do that for this program because, as you mentioned, I was just exploring the parameter space, trying to understand what it would take to do a 1,000 source survey. I don't think I wrote it in the slides, but for this particular case, since I was doing 20 arc minutes by 12 arc minutes, I did a 20 arc second grid step size. And if I was planning this for the actual proposal submission, I might make that a little bit finer, because as we saw from the plots, 20 arc seconds was kind of out at the edge, and you might be able to gain maybe 5% more sources if you take that down to 10 arc seconds or something reasonable that doesn't take forever to run. But yeah, so there's a couple of little things that you can do to increase the number of sources that you've observed in the final plan. But like I also said, that this is a statistical survey across a wide field, and that's really kind of what MPT is very good at planning.
Hi. So given the intricacies in planning the observations, right, and trying to get these targets, one thing I noticed you did not mention at all is dithers. So I'm wondering, is dithers, so there is no, is there option for dithering?
Yeah, I didn't go over dithering. I don't think I have that area captured, but what I did mention at the beginning where I described this is that I'm observing a three shutter slit with these nods. So what the nods do in that 3 shutter slit, you start off in the center slit and you take an exposure, and then you nod, I think it's to the lower slit, and you take an exposure, and then you go to the upper slit and take an exposure. So you do get 3 points in that dither pattern that's very small scale, from the center, from one shutter to the next. We do also have the option in the MSA planning tool to define dithers that construct a new MSA configuration. And so if you want to observe for 6,000 seconds in total, you could basically translate your plan to a new configuration that's some hard fixed distance away in terms of shutter space. That's what we call our fixed dithers. As soon as you add configurations, you're multiplying the number of operable shutters you need to have available, and the multiplexing does go down a bit. I didn't mention that in the multiplexing constraints, but it's something that we're starting to create those plots for to understand how the constraints on dithering will affect your source multiplexing, and it does decrease because of the available shutter area. Yeah.
Thank you.
But if you're doing something that's a deeper survey, basically what we found is you'll be able to observe the consistent same number of sources if you do fixed dithers on kind of a small scale. But like I said, we're still kind of looking into some of that.
Are there any other questions in the room here? If there's no questions in the room here, does anyone have any questions online? If you do, feel free to go ahead and unmute yourself and to ask your question. Well, it sounds like we don't have any questions online. So why don't we thank Tracy for her very nice talk. And I think our next JWST community lecture is in 2 weeks' time, and will be Eric Toulerud talking about Community Software Initiative. Okay, thanks.